Welcome. We saw that spinodal is defined as the boundary between unstable and metastable regions in a two-phase region. Okay. So, in order to understand what is this metastable, what is unstable, what is stable, we can use a mechanical analogy which is due to Kahn himself. So, it is there in one of his lectures. So, some point we will see the reference to it. And for doing this mechanical analogy, I have sourced this triangular prism. Okay, it has three sides. One side I have marked with red lines, the other side I have marked with blue lines, and this third side is open, but you can imagine that this is also closed and with green lines, for example. Okay. So, if you take this triangular prism now, and this is at its stable equilibrium, because if I try to push it like this, it will fall down, right. It will fall down to the same shape. I can push it in whichever way I want, it will always fall down to this like this. Why does it do that? It does that because the system is trying to minimize its potential energy. The potential energy is given by mgh, where h is the height of the CFG with respect to some reference. So, let us take that this is the reference on this sheet on which this is sitting, and from there you measure the CFG. When I do like this, the CFG increases, which means the potential energy increases. So, the system falls down. So, whichever way I perturb it, then it comes down to its equilibrium position. So, this is an example of stable equilibrium. Let us consider this. If I push it a little bit, it does come back to this position. So, this is also a minima, right. If I perturb a little bit, then it actually comes back to the same position like in the earlier case. However, if I perturb it a lot, then it does not come back, right. It falls into one of the other equilibria, right. All these three sides, when it sits on, it will have the same CFG. So, that is the most stable equilibrium. So, that is known as stable equilibrium, because that has the least potential energy. In the case where the triangular prism is standing, it does have a minima about this standing position, but that minima is having still higher energy as compared to the one where it is lying down like this. So, the second one, where it is in this kind of standing position, is known as the metastable minima or metastable equilibrium. If I keep it in a fashion like this, for example, if I am trying to make it stand on one of these corners, then I do not any small perturbation will always make it fall to the minimum, one of the minimum. I mean, it does not have to fall only on this side, it can fall on this, it can fall on this, or it can fall on this. Okay. So, it is a triangular prism, all three sides it can lie on, all are equivalent. So, if I keep it something like this, then it is going to fall into one of these positions. Okay. So, it will always fall into one of these positions. Okay. So, that is known as unstable equilibrium. Okay. Now, let us try to understand it more in terms of the potential energy. Okay. So, what do I have? I have these three cases. Okay. So, I have something which is like this, right, and this is metastable. On the other hand, I have something which is like that. Okay. So, in that case it is stable, and if I try to stand this on any one of these then it is unstable, because it is going to fall to either this or this, and most of the times it is going to fall to this, not this, because of the way the structure is. In terms of potential energy and in terms of the configurations, if I look at, so there is this and then there is this. Okay. So, this is metastable. this is stable, that is unstable. So, what is happening when you are like this, you know, when you have this and when you are pushing it a little bit here and there, if for small pushes, right, the system still finds that this is the minimum energy position, so it comes here. But when I am taking this and when I am pushing it beyond a point, when it reaches some configuration like this, then it is going to fall like this. So, it is going to reach this configuration when I am pushing it too far, and then it falls in this. Now, when it is in this kind of stable equilibrium, it does not matter how much I push, it is always going to go and fall into one of these equilibrium positions. So, this is how we define metastable, unstable and stable. Stable is something that can resist all perturbations that you give, right. So, if it is stable, then that has the least energy. Between stable and metastable there is not any difference. Metastable also, if you give perturbations, it will try to go back to the position, except that when it is metastable, there is another equilibrium position which is lower in energy than the metastable one. Okay. Stable is basically the least energy possible configuration of all the configurations. Okay. Metastable is locally stable, but globally it is not stable because there is something else which has lower energy than that. So, given a chance from here, it will actually fall here. Unstable is a configuration where it is not stable against any perturbation, any small this thing is going to put it into one of the metastable or the stable states. In the case of a system which is undergoing spinodal, the same thing is happening. In the case of a system that is undergoing spinodal, when the system is in the homogeneous composition state, it is like unstable state. Okay. It has higher energy, the system would like to fall into one of the metastable or stable states that is available. Okay. In fact, we are going to show it as part of the next module, that if suppose you take any property, okay, and in this case we are looking at actually free energy, but it could be any generic property, okay, as a function of composition. Okay. If this property, you know, has so let us consider a generic X property. So, it has some strange dependence, okay, so on composition. If you have something like this, you can show that whenever you pick some composition and you want to know, so suppose this is something, okay, so that is the common tangent, and so it is like this, and when you have a system like this, you try to make something from this, you try to prepare composition of this, for example, then because this point lies above this tangent that you have drawn, that will be metastable. And if you have a region which is like this, and if you try to prepare something like this which is lying below the common tangent, that will be unstable. So, this we are going to prove. Okay. As you can see, in the case of our free energy versus composition diagram, which was like that, so you take a common tangent. So, any point that lies above basically becomes unstable. Okay. So, if you take some composition and if you draw a common tangent, and you try to look at the other point which you are trying to prepare from this, whether that point lies below or above this tangent is what is going to determine whether it is going to be unstable or metastable. Okay. So, we are going to do it in a slightly greater detail and more properly in the next module, but in terms of the mechanical analogy. So, you have to think of the region where G double prime is less than 0, or where the second derivative of free energy with respect to composition is less than 0, is basically an unstable region. It is like standing the triangular prism on one of its corners. And when you have the free energy with respect to composition, the second derivative of it is positive, that is equivalent to making the prism sit or lie down, okay, because local fluctuations if you do, locally the potential energy of the system increases, so it tries to resist that. In the same way, in the system which we are considering in a binary system, any local composition changes are going to increase the system's free energy, so the system is going to resist that. it can overcome, it can go to the most stable equilibrium, the least energy configuration, but for doing that it has to overcome a barrier. Okay. So, that is what we mean by spinodal. So, miscibility gap and spinodal, in both the system would like to phase separate into A rich and B rich regions. In the metastable region, for undergoing this phase separation, the system has to overcome a barrier. In the spinodal region, it does not have to overcome any barrier, it can do it spontaneously, which means in the metastable region, the mechanism of phase separation is by first overcoming the barrier, that is known as nucleation, and then growth, which is driven by diffusion. On the other hand, in the spinodal region, because there is no barrier to be overcome, the entire transformation is completely driven by diffusion. So, this is what we are going to discuss in greater detail in the next module. We will start with this derivation. We will show that this common tangent, any point on the curve that lies below the tangent will be unstable, and any point that lies above will be metastable, and then proceed from there. Okay. Thank you.